Let's discuss a question from theory of machines. So basically, this is a question on natural frequency, and basically, not even that. It's basically the requirement is to derive a differential equation from which, again, the natural frequency and other things can be found out. So derive the equation of motion for this, for the angular motion. So what we do is, we take this rod, okay, which is in this position. Now we assume that it has moved by angle theta, okay, and then we put all the equations on this, we put all the forces on this. So here you have the hinge, so basically OX and OY, okay, and here now because it moves with theta, there is, and assuming that it's moving at certain amount of time, it is moving with theta, with some angular velocity theta dot, and with some angular acceleration theta double dot. Now because it's moving with some angular velocity, there is some velocity at this point towards the bottom, so there is some resistive damping force, because damper opposes the motion. So Cx dot, now assuming that x is the, because of theta, x is the vertical motion of this end, so x dot and x double dot is the acceleration on this point. Now because it moves down, so spring force, spring which was initially in unstretched condition now tries to apply a force opposing. So spring always opposes the stretch or the compression. So this is Kx. So I have these forces. So what we do is, now this is a body in free fixed axis rotation. So we apply sigma moment about either center or about O. Why we apply about O? Because the unknown reactions, when I don't know, I don't want them into the equation of motion. So we apply sigma m is equal to I alpha about O. So sigma m is equal to I alpha. I assume that I take clockwise direction positive. So this Kx will produce an anti-clockwise motion, Kx into length. So minus Kx into length, and the Ch is also opposing this. So minus Ch dot is the force, it is C times the velocity of the end. So it's basically the damper force is C times the velocity with which which it opposes. So C times velocity is nothing but h dot. So minus Ch dot into the length L is equal to I naught alpha. Now I naught is mass moment of inertia of the rod about the end. Now about the end it's ml square by 3. About the center it will ml square by 12. But this is about the end O. So x. Now what is x? X is the tip displacement. Now remember that this is the length L and it moves with theta. So x will be for small theta. Actually x should be L sin theta, but for small oscillations, for smaller angular acceleration, this is nothing but L theta. So when x is L theta, x dot is differentiating with respect to time, it is theta dot. Okay, so keeping everything into that, so minus k, x is L theta, so L square theta, we want to get everything in terms of theta. X dot is L square, so L square theta double dot and alpha. So ml square by 3, this is theta dot angular acceleration, bringing everything towards right, so 0 on the left. So kl square theta plus cl square theta dot. So now if you look at the values, which satisfy, this is basically the equation of motion in terms of theta. So if you compare the given answers, let's look at the options. So basically C and whatever we got are looking same, right? C and whatever we got, because they have just divided the entire thing by 4. So if you divide the entire thing by 4, which can be done without loss of generality. So if you divide everything by 4, so kl square by 4 theta plus cl square by 4 theta dot. So this is nothing but same as the C. So the answer is C. This is a simple problem, just basic mechanics you have to apply. This is a basic dynamics problem. Basically because of the motion, so you have to apply sigma m is equal to I alpha because it's in rotation. Get everything in terms of theta, and that is your differential equation of motion. Thank you.